Hello, this is video 58. I'll be talking about moment of inertia. We are continuing our discussion of the rotational equivalence of all the linear quantities we learned about previously. So moment of inertia is the rotational equivalent of mass. So I usually explain this one with a demo. I do something similar to what's in this picture, except that when I have a rod and I have weights attached on it, the weights are actually on the inside so that the students can't see them. So what I do is I rotate a rod that has two weights near the center, and I have a student rotate a rod that has two weights toward the end. And we do a race and see who can rotate it faster. And it turns out that I always win because mine is a lot easier to rotate. And you can try this at home. You can tape juice boxes on a meter stick, because I'm sure all of you have a meter stick at home. But anyway, so you know that the further away that the masses are, the harder the object is to rotate about that center point. But the mass of the two objects is the same. They both have the rod and the two identical masses. So you can see that the property that makes an object easy or hard to rotate is not just the mass of the object. There's more to it, and it's the moment of inertia. So the moment of inertia depends on three factors. The quantity of matter, so how much mass is there. You know that something that is more massive is going to be harder to rotate. But it also depends on the distribution of matter. So that's what the demonstration shows, that the further away that the masses are distributed from the axis of rotation, which is in the center here, the harder it is to rotate. And the moment of inertia also depends on the axis of rotation. So if you just have a plain old rod without any masses, and you rotate it about the center, it's pretty easy to rotate. Let's say it's a meter stick. But now you take that same meter stick and you try to rotate it about the end. So you know from experience, if you're trying to rotate this one, it's going to be harder to rotate. You can just try it with, if you have something heavier than a pencil, but you can see that it's easier to rotate when the axis of rotation is in the center versus in the end. And that's because by changing the axis of rotation, you're actually changing factor number 2 here, the distribution of the mass. In the first case, when the axis is in the center, your mass is relatively close to that axis. But when the axis is at the end of the meter stick, you have a lot of mass over here that's very far away from the axis of rotation. So the actual definition of moment of inertia is the sum of mr squared. This is only good for particles, and what I mean by this is objects that we don't care about their size or shape, that we pretend that they're very small, and so they're kind of like point masses. So just pretend that the masses are very tiny, they don't take up any space, we just care about how massive they are. And the more massive that they are, the bigger the moment of inertia. And likewise, the further away that they are concentrated away from the axis of rotation, that's the r, in this case this would be the distance r here, then the bigger the moment of inertia. The unit for moment of inertia is kilogram times meter squared. And I just want to do one thing for this first part of this video here. I want to relate this to something that you already know, just so that it can make a little bit more sense, and that is Newton's second law. With Newton's second law, we learned that the acceleration was a sum of the forces over the mass. We learned that the more massive an object was, the less the object would accelerate. So it's the same thing here. The bigger the I, the less it's going to accelerate, the harder to rotate. So when you're trying to figure out the moment of inertia of an object, look at the distribution of the mass. The further away that is distributed, then the harder it's going to be to rotate. That means you have a greater moment of inertia.